In this video, we're going to learn about calculations regarding concave mirrors. Our mirror equation is 1 all over f is equal to 1 all over do plus 1 per di. If we're going to declare the following variables, do stands for object distance. This is the distance between the object placed in front a concave mirror. On the other hand, di is the image distance or the image formed between this distance up until the concave mirror. The focal length f is the half of the radius of a concave mirror. The radius of the concave mirror, as you can see in the diagram, this is the length between the point C up until the edge of the concave mirror. If we're going to have that, that is already the focal length f. Now we have the second equation as the magnification equation, which stands at letter M. Magnification now is equal to the height of the image per height of the object, which is also equal to the negative value of the distance of the image per distance of the object. Now let's proceed with the first sample problem. A 4 centimeter tall light bulb is placed a distance of 45.7 centimeter from a concave mirror having a focal length of 15.2 centimeter. Determine the image distance and the image size. Now we are given with the following variables as the height of the object at 4 centimeter. The distance of the object is placed 45.7 centimeters and our focal length is at 15.2 centimeters. Now we are going to determine the image distance or di and the height of the image hi. Our solution proceeds as we're going to use the mirror equation at 1 per f is equal to 1 per do plus 1 per di. If we're going to plugging in the values, 1 all over f is at 15.2 centimeter, which is also equal to 1 all over 45.7 centimeters plus 1 all over di, or the distance image, or the image distance. Now, if we're going to further simplify the following quantitative values, this gives us 0.0658 per centimeter is equal to 0.0219 per centimeter plus 1 all over di. If you further simplify the following quantities, this gives us the following. Our image distance is equal to 22.8 centimeters. For the magnification, we're going to use this equation to determine the height of the image. Our magnification m is equal to hi per ho, which is also equal to the negative di all over do. If we're going to plugging in the values, okay, so we are given with this side for hi all over ho at hi per 4 centimeters, which is also equal to the negative value for the solved image distance at 22.8 centimeter per 45.7 centimeter for the object distance. Further simplifying the following quantities, if we're going to cross multiply 4 centimeters to the other side of equation, this gives us the following quantity as negative 4 centimeter times 22.8 centimeters divided with 45.7 centimeters. Further simplifying the following values gives us for the height of the image is at negative 2 centimeters. So why is it negative? It is negative because the formed image is an inverted one. Now let's proceed with the second problem. A 4 centimeter tall light bulb is placed a distance of 8.3 centimeter from a concave mirror having a focal length of 15.2 centimeter. So we're going to note that this second problem differs from the first problem by virtue of the distance of the object. Okay. So this is the same object and the same mirror. Only this time, the object is placed closer to the mirror. So we are given with the same value as the height of the object at 4 centimeters. and the focal length of the concave mirror at 15.2 centimeters. The only change variable here is the distance of the object from the concave mirror, which is nearer at 8.3 centimeter. Take note that the distance of the object is lesser than the focal length of the concave mirror itself. Now, if we're going to declare the following variables, we are given with the height of the object at 4 centimeters, the distance of the object at 8.3 centimeters, and the focal length at 15.2 centimeters. And we have the following unknowns as to determine the image distance and the image size, or DI and HI. If we're going to proceed now with this solution, we're going to use the mirror equation at 1 per F is equal to 1 per DO plus 1 per DI. If we're going to plugging in the values, this gives us 1 per 15.2 centimeters is equal to 1 per 8.3 centimeters plus 1 per the distance of the image. Further simplifying the following quantities, this gives us 0.0658 per centimeter is equal to 0.12 centimeter or 0.12 per centimeter plus 1 per di or the distance of the image. If we further simplify this, if we transpose 0.12 to the other side of equation, this becomes 0.0658 per centimeter minus 0.12 per centimeter or negative 0.0547 per centimeter and equated to 1 per distance of the image. Solving now for the distance of the image gives us negative 18.3 centimeters. Now, if we're going to solve for the image size or the image height, we're going to use the magnification equation at HI per HO is equal to negative DI per DO, or HI per 4 centimeter is equal to negative of the negative 18.3 centimeter per 8.3 centimeters. We're going to cross multiply 4 centimeters to the other side of the equation. This becomes negative 4 centimeters multiplied with negative 18.3 centimeters. So this is the solved value for the image distance divided with 8.3 centimeters, or this is the object distance given. Now, further simplifying the following quantitative values gives us 8.8 centimeters. Now, we're going to proceed with the sign conventions for the mirrors. If the focal length F is positive, the mirror is concave. If the focal length is negative, the mirror is convex. On the other hand, if the distance of the image is positive, the image formed is real image and it is located on the object's side of the mirror. On the other hand, if DI or the distance image is negative, the image formed is a virtual one, okay? And it is located behind the mirror. If the height of the image is positive, it is an upright image and also virtual. On the other hand, if HI or the height of the image is negative, the image formed is an inverted one and it is also real. Our next video tackles about convex mirror.